Alright, here, I know there isn't anyone in the call or probably watching the stream right now, but here is the classics technique lecture. So, contents for today, we have binary search, sliding window, me in the middle, and line sweep. So first we're going to play a little game to help us familiarize ourselves with binary search. So, alright, Wei Lian, I am thinking of a number between 1 and 100. You can ask me any yes or no questions. So you can basically ask if it's more than something, and I'll tell you if it's too high or too low. And then try to get this number in the fastest way possible. Wei Lian.
Hi, I'll start with 50.
Alright, it's too high.
Too high, then I'll choose 25.
Alright, that's too low.
How about 37?
That's too high.
How about 31?
That's too high.
Still too high. 28.
That's too low now.
30.
That's too high.
29.
Yep, that's it. Yeah. So basically you guess the middle number of a thing, and then if it's too low, you just guess the upper half, and if it's too high, you just guess the lower half. So basically what this does is that every time you ask a question, you cut the possible range by half. So if the entire possible range is like n, you can find the thing in O log n time. So this is a bunch of text, probably copied off Wikipedia. Yeah, that's probably it. So yeah, basically it halves the search space with every time you ask a question. So it is much faster than just asking is it 1, is it 2, is it 3, because that's O(n) time. So here's a demonstration of how fast binary search is. Sorry. Yeah, we found it in just 3 steps, but if we try to find everything one by one, it's going to take us very long, and we don't want that. Alright, so basically here's the code. You basically have a low and you have a high, and then while the high minus low is more than 1, you just take the middle is basically the middle of high and low, and then you check if the middle is more than x, and then basically if it's too high, you basically set your high to mid, and then you go back, and then if it's too low, you set your low to your middle, and then after everything you just find your low. But I'll get scammed, because if you're trying to binary search on an array, you can use upper bound or lower bound, and it basically does the binary search for you, and you don't need to implement this. And this also works on a set or map, but it works a bit differently. But alright, so I get scammed again, because even though you have these STL functions that can do binary search for you, you still need to remember this template, because there are some questions. Because what this allows you to do is try to binary search on an array, but not every time you have a array to binary search. So let's say if you are trying to find the answer to something, and then it's very slow to calculate the answer directly, but checking the answer is quite fast, then you can use binary search to basically guess the answer, and then use your fast checking to basically adjust it. And if you're trying to do that, you're going to need this code. So you might have noticed one thing. This only works if A is sorted. So basically in your array, if you're trying to binary search an array or vector or deck, you have to make sure that it's sorted first. And then because like set and map are sorted by default, so you don't have to worry about that. But what if you're trying to do what I said just now and binary search the answer, which is something that you don't know. There's no array. Basically in this case, you have to make sure that your answer, that basically the answer is monotonic. Yeah, it's basically this. Monotonicity. So yeah, basically here's something that I probably don't understand. So basically like, because if we go back to our, let's say the guessing a number question, if I say like, if Wei Lian asks me 50 and I tell him that's too high, he basically knows that if 50 is too high, then 51 is definitely too high, 52 is even more definitely too high. So basically like, you can think of that as monotonicity. So if 50 is too high, you know, maybe 49, maybe it's okay, but 51 is definitely not okay. So basically that's monotonicity. So basically, yeah, monotonic is either like non-increasing or non-decreasing, as you can see in this thing. Yeah, so like this, like it's quite hard to explain, but it's like you just like read the slides and you probably can understand. So like basically binary search only works if your function is monotonic. So now we're going to because there's nobody here. Is there anyone watching the stream? There's only one guy watching the stream. It's probably me. So if there's no one watching the stream, we're not gonna give you time to do it. We're just gonna explain it. So basically you have like n boxes of iPads, and each box have a certain number of iPads, and then you want to distribute the iPads to k people, and then each person only gets a consecutive range of boxes. And then you want to minimize the unfairness, so you want to reduce the maximum number of iPads each person gets. So for example, if this is our array, you have n boxes and each box has like the number of iPads labeled on the screen. You need to distribute it to 3 people. Here's one possible way. So the answer in this case is 17. But basically but we are trying to implement this using binary search. So let's assume that, let's say we want to target that each person gets a maximum of X iPads, and then whether is it possible to distribute all the iPads in this, assuming that case. So yeah, we have basically a query and a response. Yeah, so we in this case we also need to take greedy. So let's say the number we're guessing is 15. We're trying to binary search the answer and we guessed 15. So we want to see if it's possible for each person to have at most 15 iPads. So you just keep taking until you can't take anymore. So like you take 3, you take 4, and then you take, and then you take 3, 4, 2, and 3. So that gives you a total of 12. And you can't take anymore because the next one is 6. So if you take that, you're gonna have more than 15. So the first person takes that much, and then the second person takes 6 and 5, and then the third person takes 10 and 5. But wait, we have an extra that's not taken, so it's not possible. So it's not possible. We need a fourth person, but we only have 3 people. So x equals 15 is not possible. So that means that x is actually too low. So we need to binary search the answer. And x has to be higher. But how do you know that? Because remember the thing about, if 50 is too high, then 51 is most definitely too high. So in this case, it's the same. If 15 is too low, then 14 is gonna be even worse. So we don't even need to think about it. We can just jump up. Yeah, so basically that's how monotonicity works. So if a certain x is possible, then anything more than it might be possible. But if something is not possible, like in this case 15 is not possible, then anything less than 15 is most certainly not possible. So basically that's how you use it to solve this question, to binary search. Basically, yeah, so you need it to be monotonic, and you need like I said before, a fast way of checking if your answer is correct. Alright, should I just show them should I just like show a sample code on stream? I think I should. Yeah, so like, yeah, basically like, because we have like, we don't need to wait for them to do the question, so we have like copious amounts of time. So like we might as well just like try to go through the question, go through it. So right,
We have like a lot of time.
yes, we have way too much time. Hold on, let me find it. Let me find my.
They just pause the video themselves if they want to do it.
Yeah, so like, alright guys, if you want to like try out the question, like pause the video right now. Wait, let me check if there's people watching first. There's like one. Alright, that's great. Alright, let me find it.
2-1. Where even are the advanced people? Why is elementary 4 people and like advanced 1 nothing?
Alright, it's fine. Like we should like I think you should go ping them and then like ping the North Coast trainees and then like get them to join. Like I hope that works.
Pin everyone.
Alright, so like, can you guys, alright, you can see this. Alright, so basically we have our n boxes and we have our certain number of iPads in each boxes. Bro, this code is like so old. Alright, and then you have basically your upper and lower for your binary search, and then your middle. And then basically in this case we just like take the upper as the maximum number of iPads possible, total iPads possible, and then we just start binary searching from there. So basically let's say the mid is basically the number we are trying to guess. So like in the number guessing game, that will be 50, but in this case it's going to be half the total number of iPads. So basically for all the boxes, we can, if basically we are trying to do greedy, so if the taken is basically the number of iPads that the current person / squid is taking. So if we add our current box of iPads to it and it's less than the number we're guessing, we can just do that. We just add. But if we cannot, that means we need a new person. We need a new person to come in. So we reset our taken value to 0. We get the new person to take the iPads, and then we just increase the number of people we need by 1. So basically, if we need more people than the number of people we actually have, which is m, that means that our mid value is too low. So in this case, we'll just put our lower. We'll just set our lower as the mid, we'll set like the new. I'll set the middle as the new lower bound, and then otherwise we just set our upper as we just set our middle as the new upper bound. And then basically here's like a little tip and trick for me. Like if you're confused like whether to like see out lower or see out upper at the very end, you can just see out and just like see out everything, and then like check, and then pick the right one before you submit your solution. So like that's like a smart tip. And then once you find out which one is the correct one, you can just put it there. So basically that's the entirety of the code for Schizophrenic. It's actually like binary search is your like at the beginner / slight advanced level. Like at this level is going to be quite common. There's quite a lot of questions for it. Like if we alright, let me switch back to our browser first. Yeah, there's quite a lot of binary search problems. Like basically we have Schizophrenic, this. So like there's quite a lot. Yeah, so like this, you can see that there's a bit of binary search here as well. And then this question is all of these are all binary search questions. Alright, I'm just going to take a break before I'm gonna get some water, and then we're going to move on to a sliding window. Alright, so like while we do this, while I go get my water, you can look at this question, flamethrower, first. Alright, hello, welcome back. Now we'll be going through sliding window. So like, first we have this problem flamethrower where we want to pick a continuous subsequence of length k such as the sum of all the elements is maximized. So like we could just brute force every possible combination. So there's like n possible combinations and we have to like add up k numbers for everyone. So like that's gonna TLE. But like technically no, but since the limits are quite small, like n and k are quite small, it's like you could just brute force nk, but that's not what we're here for. We need to like, even though it can AC, we still need to like try and get the lowest timing possible because we are all like CP students. So basically, let's say our n is 8 and then our array looks like this and we have a k of 4. So like these four numbers add up together is 10, and then let's say we want to move on to the next number. We can just slide it by, because these, you notice how these three numbers actually don't change. We just added this 5 and we took away the 1. So this allows us to transition in, this allows us to basically like go on to the next one in O1 time instead of OK time, because we don't have to calculate the entire subsequence. So like in this case we just add 6 and then we minus away the 3 and then we get 17 and so on. And then basically at every step you just like have a let's say your answer value, and then your answer equals maximum answer and then your current value. So like that's easy. But what if our window size is not constant? So here's a new question, which is lineup. So basically you have n cows and each cow has a specific breed, and then each cow also has a specific coordinate, basically their position, and you want to take a photo such that you have every possible breed of cow in the photo in the range, and then you want the minimum possible cost. So in this case our window size isn't constant. But what we have to observe is that if a range L to R satisfies the requirement that we need like at least one cow of every type, then L minus 1 to R or L to R plus 1 also satisfies this problem. So like it's monotonic. That's crazy. And then so basically we just have a pointer. We have basically two pointers and it moves along the array. So if we don't meet the requirements, we just like move our right pointer to the right to try and like extend. So like initially both the left and right pointers are at the very start, and then if it doesn't meet the requirements, we move the right pointer to the right to try and like expand our range so that it is going to meet the requirements. And then because since we are trying to get the shortest possible length, so like the shortest possible like R minus L, so once we hit something, once we move our pointer R, our right pointer R to the right for like a certain time, and now we find out that hey, now the L to R actually fits our requirements, so we basically like record down like the R minus L, and then we just keep track of it, And then because since L to R already fits the requirements, there's no point extending the R pointer any further, because you're just you're just making it less efficient, like you're giving yourself a worse answer, because like L to R already satisfies the requirement. So like L to R plus 1 is still gonna satisfy the requirement, but it's going to come at but it's like less good, because you're getting like one more. So once you satisfy the requirement, you just, instead of moving the right pointer, you move the left pointer, and then you move the left pointer until it doesn't satisfy the requirement anymore, and then you start moving your right pointer to the right again. So basically you just keep doing this. So like, and in order to keep track of like the type of cows, we can use your set and multi-set. So like we use the sample test case for lineup as an example. So let's say the yellow thing is our range, so like our left L to R. So in this case, like L is at the first, L is 0, R is also 0. So we move it along. We use a set and multi-set to keep track of the cows. And then once we expanded our R all the way to position 0, 1, 2, 3. So after our R reaches position 3, we now have a full set. So we just update our answer. So like it's gonna look something like this. So now it works, because this is how we keep track of it. So basically the multi-set, we keep track of the exact numbers, while the set, because a set has no repeats, so we can use it to keep track of whether everything is there. So we just like use set.size, like s.size. So now after this, we just because since like 0 to 3, like left pointer at 0 and right pointer at 3 already fulfills the requirements, we just start moving our left pointer to the right. So in this case, we remove the first one from our multi-set, and you can see in this case, like, hey, it still satisfies the requirements. So we just update our answer again. And then you can see it's like clearly better, because like the distance of 10 is worse than this distance of 5. So that's good. So because this window still works, we increase the L, we move the L left pointer again. So in this, we increment this and we remove this 1 from our multi-set. But in this case, we check our multi-set and we find that, hey, 1 doesn't exist anymore. So we have to remove this from our set. So this window doesn't work, so we can't use it. So now we just start increasing our right pointer again. And then look, oh, it works again. So now we have 26 minus 22, which is 4. So that's going to be our best possible answer, which is also what we see here, 4. And then yeah, that's basically the sample code for lineup. Alright, moving on, we're going to this question flamethrower X extreme. So it's actually not the same, which is crazy. Yeah, but basically in this case you can, instead of having a fixed k, you have a, instead of a range of k, you can have a range of up to k. So plus the cost can be negative. So yeah, we are not gonna go through the brute force part, but basically first, basically for the one, we only want to go for the the last subtask where there's no data constraints. So basically what you can do is, instead of a sliding window, we have to, for this question we have to use the sliding deck. So basically first we use a prefix sum to basically allow us to like quickly get the to like find out the sum of a range. And so like I think, wait, someone joined. Oh, hi Siram.
It's just me. Why is there like literally no one? What's going on?
There's literally no one.
I have no idea. There's like 0 trainee.
Yeah,
It's
like
all the trainers.
you look at the stream and there's one person watching, and like that person is me. And like yeah, so we're just like recording, we're just doing like a recorded lecture, like.
Oh,
They don't even watch the recording. That's the point.
bro, I bet if they don't even care about coming here, right? Do you really think they'll actually watch the recording? Who has time to watch the
No,
recording?
like Siram, you're live on stream right now. I don't think you should say that. It's fine. Like you just go teach beginner. We can just like record. We can just record the lecture, and then like they can watch it if they want. If they don't want, we're not gonna chase them. We don't have time to chase them.
Chin. Okay, I'll go back. Bye.
Alright, bye bye.
This is so wow.
Alright, so like back to our
He went back to elementary.
back to our visualization. So like let's say this is our array, and then we have our prefix sum array. So like this is like a recap on prefix sum. If you don't know, basically you're finding the sum of any range. So like because we want to maximize our values, and the prefix, how a prefix sum works is that you have like you have the thing on the right minus the thing on the left. So I have the purple thing minus the green thing. So if, let's say for a fixed purple thing, and then since you want to maximize the value, you want the green thing to be as small as possible. Yeah, that's it. So like basically for each I, find the minimum of all the prefix sums, and then but you must also make sure that it fits within the maximum range of k. So like let's say we are currently at index 4. So if we want to find the largest possible value, we look at prefix sum of this to find the minimum. So like in this case, because we are minusing off this green value, so we want the green value to be as small as possible. So in this case, we choose 4. So like 6 minus 4 equals 2. And then basically we just do the same thing for all the possible indexes. Yeah, but this is not the full answer yet, because the trainer is very scam, and then they didn't let multi-set AC. So bruh. So yeah, as I said before, you have to, I wasn't crazy. You have to use a sliding deck. So basically we just keep a deck, and it keeps track of the useful index Yeah, it's the index. Remember, it's the index, like not the value. And then you only keep the useful ones. And then, so like, for the range, to keep track of our range of k, once the front element gets out of range, we just kick it out. And then like, when you have useful values, we push new index to the back. So like, if we have our array and then we have our deck. So first we start at hold on. Yeah, so basically we just keep track of, want to find the minimum possible value. So in this case, first we start off at 11, and then because like it's the only thing, so we just push the index of 11, which is 0, into the deck. And then we go on to the next one. Because 1 is less than 11, so it's better. So we just replace the index of this with 1. And then the 8, for 8, because it's more than 1, so we push a new one we just push the new one into our deck. And then now we arrive at 4, and it's better than 8. So we push an index of 4, which is 3, into the deck. So our minimum is basically the minimum in the range of 0 to 3. This range is going to be 1 because it's here. So the array 1, so it stores the index of the minimum value, which is 1, and the value is also 1. And then let's say we move on, because now we have a 2, because 2 is less than 4, so it's better. So we replace the index 3 with index 4. And now we move on. So now two things have happened, because this 1 went out of range, so we just kicked it out. So it becomes from 1, 4 to just 4. And then because we have a 9 here, we push the index of 9, which is 5, into here. So like, and then basically at every step we just like take the minimum. We just try to find the minimum of the range. So like, now back again, 1 is better than, basically we have 4 and 5. And then now it gets like interesting, because we also, for this next step, we also do two things at once. So we have this new 1 into our table, because you can see at first it has the index 4 and index 5, which corresponds to the 2 and the 9 in our array. So because 1 is better than 9, so we replace the 5 we kick out the 5. And then because the 1 is also better than the 2, we also kick out the 4, and then we replace this with 1. So our index, the deck, is 6. So this is basically how we keep track of the minimum values. So basically, in this case, basically everything, the index at the front of the deck always points to the minimum value, which is what we want. So that's basically how a sliding deck works. And then now we'll basically like put it together with everything else. So we compute the prefix sum of all the values, and then we keep track of the indexes of the minimum prefix sum with it. We use our sliding deck to keep track of the index of the minimum, because remember the purple minus the green, we want to basically make sure that we minus off the smallest possible. And then we find the maximum possible value of trees. So like this sample code. So basically the I in this sample code is like the current tree we are at, and then so basically we want to push the current value into our deck. So remember, like the one where you see the 1, we're trying to push 1 and it knocked both the 2 and the 9 out of our deck. Basically that's the first part, while the value of the index that's stored in the last place in the deck is, it's like, let's say, because like in this case our pre-I is going to be 1, and then a pre of the deck dot back is basically 9. So because since 1 is less than 9, we just pop up the back, and then we just keep doing this until it isn't, and then we push the index 1. We just push like the index of 1, which is 6, back into the deck, which is this step, the dq.pushback. And then we also need to make sure that nothing goes out of range. So if it's out of range, we just pop front. And then since like the dq0, which is like the front of the deck, carries, and then the index points to the smallest possible number in that range, we use our prefix sum to calculate the prefix of I minus the prefix of this, and then you take the maximum, and then that's your answer. So yeah, that's it for sliding window, and then we'll take a short break and then go back to meet in the middle. Okay, while I take a short break, you can look at this question first. Alright, okay, welcome back. Alright, now we have meet in the middle. So it's basically brute force but smarter. So we have our force. Yeah, we have force. Yeah, we have force. We have our for sum question right here. So basically we have four arrays, and then you need to pick one number for each array such that so that the sum is equals to 0. So like the most obvious brute force is to just pick every single possible combination of 4 numbers. So like O(n) to the power 4. Womp womp TLE. Alright, so we observe that if we want like have x and y equals 0, y must be equals to negative x. That's quite simple to understand. So what if we split our numbers into two groups? So let's say a plus b is one group, and then c plus d is another group, and then they add to 0. So a plus b must equals to c plus d, as like equals to negative c plus d. So, and then if we want to, we can brute force each one of them in O(n) squared time. So like after, yeah, so we just use O(n) squared to brute force every possible sum of the numbers in a plus b, and then every possible sum in c plus d. And then after this, but how do we combine them? If we want to like try every pair again, we want to do another brute force. Let's go to O(n) squared, and it's still the same as before. So we need to, but if you notice that if we sort our arrays, the values become monotonic, so we can binary search. So basically, let's say we binary search, we sort our c plus d, and then we have our a plus b. So for our a plus b, we just check to see if there's a corresponding c plus d value such that like it adds up to 0. So we just binary search. So you have x in the first array, we binary search for negative x in the second array, and then yeah, that's ace. Yeah, we can O(n) log n ac now. Alright, so like yeah, that's actually the end of the slides. So I'm just gonna create a problem list. It's technically n. Alright, so like as William mentioned, it's technically n squared log n squared. But if you actually if you have learned like year 3 math, it's like you know that when you log something, like the base, so like log n squared becomes 2 log n. So that's like it becomes a constant factor. So it gets simplified to log n. I heard. Yeah, I'm just going to find some problems, and then if someone happens to watch this stream and they want stuff to do, they can do it. Like also like for remember if you remember the like the bitmask brute force problems that we did from before, remember how like the you couldn't like fully AC them because the n was 40, because and then your bitmask brute force can only brute force up to 20 before you TLE. So like yeah, that's something that you can use meet in the middle to solve. You can basically split them up into 20 and 20 bit, like brute force them separately and then come back and then put them together. So yeah, that's basically how you get the full solution for